Okay, let's take a peek at this one. Let's see what you got for the first one. So if V is 12, that's going to be 12 squared over R is 9. Order of operations says we have to do what first? Exponent. Well, we have to do, because of the fraction bar, we have to do the top first. And on top, we have to do the exponent. So it's going to be 144. Nothing else to do on top. Is there anything to do on bottom? Nope. So we're just going to divide. You got it. 144 divided by 9 is 16. So that becomes 16. The second one. A is 17 plus B is 31. Divide by 2 and then times H is 12. So we have the enclosing symbols, the parentheses. So we work inside the parentheses first. What do we have to do first inside there? You got it. We got the fraction bar is another enclosing symbol. So we have to do on top again, which is going to be what? Which? 48. Perfect. 17 plus 31 is 48. Now we can do 48 divided by 2, which is 24. Then times 12, which is 288. Any questions? Okay. Any questions off the homework from last Wednesday? Doing okay? Okay, well, I believe I mentioned it last Wednesday, but just a reminder, this first hour today we are finishing up Unit 1, which means in our second hour. I always hate having it set up this way, but we will be doing our Unit 1 test. So just so you're prepared. We do have one last topic to cover, though, before we do that, and that is something called a factor. A factor is going to be very important for our next unit of the class. It is just a number that will divide another number evenly. For example, 12 has several factors. What are some numbers that will divide into 12? 4, 6, 2, well, 1 will divide into it, but 1 divides into anything, so we don't count the 1. 3, you got it. And of course 12 itself, but again, any number can be divided by itself, but we don't count that because it's insignificant. Now, so these are all what we would call factors of 12 because they'll divide into 12 evenly. Technically, the technical definition of factors are smaller components that can be used to build a larger object or a larger device or whatever. In math, that would be numbers. So factors can come in pairs. So like for 12, we could have several factor pairs. We would have 2 times what would make 12? 6. Or 3 times 4. Again, we don't count 1 times 12 because that just doesn't, no advantage to using that. So when I ask you to factor something, how do you know which one we're looking for, the 2 times 6 or the 3 times 4? Well, we really don't. So normally what we do is we ask you to do something called prime factoring, which we'll look at in just a second. Now, let's go ahead and look at prime factoring. What prime factoring is rather than breaking it down into factor pairs, you break it down into the smallest possible numbers that can be multiplied to make it. Again, we don't count 1 because you multiply by 1, it won't change anything. So for 12, it would technically be 2 times 2 times 3. If we multiply those together, we get 12. There are no smaller numbers that we could multiply to make 12. So before we get too far into this, I wanted to find something called prime and composite. for you guys being in welding, you may run into the term composite with your materials as well. Something that is a composite material, or something that's just plain composite, is made up of other things. You know, composite materials might be a mixture of metals and ceramics for your ceramic material. It might be just a mixture of different types of metals for alloys and stuff like that. So composite means made up of smaller components. 12 is a composite number because it can be made up of smaller numbers. So made up of factors. It's composite. Prime has no factors. Again, excluding 1 in itself. But we don't include those again because they just really don't add anything to the whole situation. So tell me, prime or composite? Is 9 prime or composite? It's composite. 11. Prime. 15. Composite. 17. Prime. 29. It's prime. 51. This one's very commonly missed. It's composite. 3 times 17. 51. A lot of people that get in that rut, because 31 is prime, 41 is prime. So 50, 61 is prime, 71 is prime. So I think 51 has to be prime, but it is actually composite. So to define the prime and composite numbers, and to get back into our prime factoring, it would be nice if we could look at a number and have a very quick way of telling what it could be divided by. So let's take a quick look at divisibility rules. How can I look at a number and very quickly tell if it's divisible by 2? It's even. And by even, of course, we mean the last digit is 0, 2, 4, 6, or 8. So I might have a number like 73,954. All we care about, if we're looking to divide that by 2, is that last digit. It's a 4, so the whole thing can be divided by 2. Does anybody know how to tell if something can be divided by 3? Look at the sum of the digits. Let's do the 73,954. If I add up the digits, what's 7 plus 3? 10 plus 9? 19 plus 5? 24 plus 4? 28. Is 28 divisible by 3? No, it's not. So this number is not divisible by 3. However, 73,953, if I add that up, 7 plus 3 is 10, plus 9 is 19, plus 5 is 24, plus 3 is 27. Is 27 divisible by 3? Sure is. Okay, the cool thing about this is if you're not sure, what's 2 plus 7? 9. Is 9 divisible by 3? Yeah, well then 27 is divisible by 3, and 73,953 is divisible by 3. So let's add up the digits. To tell if something's divisible by 4, generally I don't care, because if it's divisible by 4, it's divisible by 2, and I just divide out the 2 twice. It's usually easier. But there is a rule that you can tell it's divisible by 4, and it's the last 2 digits. If the last two digits are divisible by 4, then the number is divisible by 4. What do I mean by that? Well, here, I got 73,952. All I care about is the last two digits. Is 52 divisible by 4? Yes, it is. So that whole number is divisible by 4. Now, the only problem with that is it requires you to either be able to quickly calculate or to have memorized all the multiples of 4 from 0 to 100 to look at it and know if it's divisible by 4 quickly. What I always do is this. I divide it by 2 and then divide it by 2 again, because I'm really good at cutting things in half. 52 divided by 2 is 26. I can divide it by 2 again to get 13, so it's divisible by 4. I can divide it by 2 twice. But my attitude is if I'm going to divide by 2 twice, why don't I just divide by 2 twice and forget about whether it's divisible by 4. For 5, anybody tell me how you can tell if a number is divisible by 5? Ends the last digit. You got it. Last digit is 0 or 5. So here, 73,985. We don't care about anything except for that last digit. Since that is a 5 or a 0, it's divisible by 5. How about 6? Anybody tell me if something's divisible by 6? If it checks out to be divisible by both 2 and 3, it's divisible by 6. Again, my attitude is if I'm going to check both of them, why don't I just divide by 2 and then divide by 3 again, and I'm good to go. But let's do an example here. So looking at this one, now I always check by 2 first because checking for 2 is really simple. Is this divisible by 2? Yeah, the last digit's even, so this is divisible by 2. So then I check to see if it's divisible by 3. So 10, 19, 24, 26. Is that divisible by 3? No. So this is not divisible by 6. It's divisible by 2, but not by 3, so it can't be divided by 6. Seven. Anybody know how to tell if something's divisible by 7? I ask that every year, hoping somebody will give me an answer, and I don't get one. There is no rule to quickly tell if something's divisible by 7. If you can come up with one that'll work every time, let me know. I'll give you an A in the class. I'll publish it and retire. I'll mention you in the byline somewhere, don't worry. You have something divisible by 8. Again, dividing by 8, you can divide by 2 3 times. You just divide by 2 over and over again. So it's not horribly important. But there is a rule. It involves the last 3 digits. So if I'm looking at 73,952 again. What it involves is looking at the last 3 digits and seeing is that divisible by 8. How many of you know off the top of your head whether 952 is divisible by 8 without punching your calculator? It is, but most people wouldn't know that. This rule is not terribly helpful at all because it requires you have your multiples of 8 memorized from 0 to 1,000, which if you did, I'd be a little worried about you, to be honest. Anyway, again, for 8, I just divide by 2 over and over again, and you take care of the 8s. 9, anybody know the rule for 9? Same as the rule for 3, basically. It's the sum of the digits. So my 73,953, is that divisible by 9? Well, 7 plus 3 is 10, plus 9 is 19, plus 5 is 24, plus 3 is 27. Is 27 divisible by 9? Yes, so that whole number is divisible by 9. Now again, If it's divisible by 9, it can be divided by 3 twice. So you don't have to know the 9, just divide by 3. 10. Last digit is 0. Good. Now, realistically, out of these, I mean, there's rules for every number from 2 to 10 except for 7. The ones that I use are the 10, just because, hey, if something ends in 0, it's really handy to be able to divide it by 10. I use the 5, and I use 2 and 3. And generally in that order, if I'm looking to divide something out, I'll see if it has a 0 or a 5, so I can see if I can divide by 10 or 5. And then I jump to the 2 because I'm just looking at that last digit to see if it's even. And then I'll look at the 3s because the 3s take a little more effort, so I don't look for them until the end. And the reason I do that is as you start dividing a number down, as it gets smaller, it starts to be easier to see what it can divide by. Sometimes you can just look at it and tell. There are divisibility rules for larger numbers, but as you get bigger than 10, it gets to be really weird. Like 12 and 15, you don't really need divisibility rules for because you just divide by, for 12, you can divide by 2s and 3s. For 15, you can divide by 3s and 5s. So it's only really necessary to have divisibility rules for what's called your prime numbers, the 11, 13, 17, so on. There is one for 11, and I'll show you. You don't need to write this down if you're taking notes because I'll never ask you to do it. Just wanted to show you this. As you get larger and larger numbers, the rules get more and more complex. So let's say I have 2,837,683. If I want to see if this is divisible by 11, I'm going to take every other digit. So 2, 3, 6, and 3, and I'm going to add them up. So 2 plus 3 is 5, plus 6, 11, plus 3 is 14. Then I take the digits that are left, 8, 7, and 8. 8 plus 7 is 15, plus 8 is 23. Now, the difference between them, so I got the 23 minus 14 is 9. The difference between them is 0 or divisible by 11, then the whole number is divisible by 11. Obviously, this one is not divisible by 11. But 2,837,681. I go 2, 3, 6, and 1 makes 12. 8, 7, and 8 is still 23. The difference between that, 23 minus 12 is 11. So that would be divisible by 11. You can see that's complicated enough that why would you bother? I mean, we do have calculators now. You can just punch in your calculator and divide by 11 and see if it comes out to a decimal or not, right? There are ones for 13 and 17 that I know of, but they get even worse and uglier, so we're not going to talk about them. So the question is, why are we doing this? Well, because we're going to prime factor. And when I go to prime factor a number, it makes the process a lot faster if I can look at that number and quickly tell what it's divisible by. So I might look at 144. If I want to prime factor that, what I'm doing is I'm going to list out the smallest numbers I can multiply together to make 144. Well, the simplest way of going about this is something called a factor tree. What is any number that divides into 144? 2, perfect. I usually go 10s, does it end in a 0? No. Well, then 5s, does it end in a 5? No. Then I go 2, is it even? This is even. So it can be divided by 2. So what I'm going to do is I'm going to split it up into 2 times, what's 144 divided by 2? 72, perfect. The 2 is prime. It cannot be divided into smaller numbers, so I'm going to just circle that. 72, however, can be divided into smaller numbers. What's any number that goes into 72? Well, it's still even, so you could go 2, right? If you could go 3, because if you add them up, you get 9. The larger number you do here, the shorter the factor tree gets. So I'm going to go with 2 and just show you how it works, and then we'll come back and try it with a different number. Divide by 2, I get 36. 36 can be split up into 2 again, and 18. 18 into 2 times 9. 9 into 3 times 3. So I end up with, I have 1, 2, 3, 4 2's. 2 times 2 times 2 times 2, and then 3 and 3. So times 3 times 3. That is the prime factoring of 144. Now let's go back here. What if we had split this up differently? What if I looked at 144 and said, hey, 144 is 12 times 12. Then 12 is 3 times 4. 3 is prime. 3 times 4. 3 is prime. 4 is 2 times 2. 4 is 2 times 2 again. I still have 2 times 2 times 2 times 2 times 3 times 3. It just was a little bit shorter factor tree, is all. When we're talking about fractions and reducing fractions, the same thing. It doesn't matter whether you divide by a big number or a small number. You're going to get there eventually anyway. But it's easier if you divide by a larger number first. So back to this here factoring. 2 times 2 times 2 times 2 times 3 times 3 is just fine if you write it out that way, but there's a shortcut. 4 2's multiplied together is 2 to the 4th. 2 3's is 3 squared. If you wanted to write it that way, you're more than welcome to. They mean the same thing. So in your notes, I want you to try to factor one for me. I want you to factor 180 for me. Give me the prime factors of it. Okay, so 180. I start out with my tree here, 180. What's one number that can go into 180? 10. I see it ends in the 0, so 10 would be a good spot to go. If I divide by 10, I'm left with 18. Good. 10 can split into 2 and 5, 5 and 2. They're both prime, so I'm going to circle them. 18 splits into 6 and 3. The 3 is prime, so I'll circle that. 6 splits into 2 and 3. Now again, I'm going to put them in order from smallest to largest. So I've got 2 and 2 there. Then 3 and 3. And then the 5. So I could leave it as 2 times 2 times 3 times 3 times 5. Or I could do 2 squared times 3 squared times 5. That is my prime factor. If you're unsure as whether you did it right, you can always multiply them back out and make sure it comes back out to 180. So now the question is, why is this important? Well, what we've been doing here is factors. So let's talk about something called greatest common factors here. Greatest common factors, we're looking at two numbers, and we're finding the largest number that can divide into both of them. So let's say I have the 180 and 144. I want to find the largest number that will divide into each of those. Well, I know they're both divisible by 2. If I look hard enough, they're both divisible by 6. 12. Is there anything bigger? Well, the way to check is this. Go ahead and just factor them. 180 was 2 times 2 times 3 times 3 times 5, right? 144 was 2 times 2 times 2 times 2 times 3 times 3. When it's prime factored, any common prime factors will be part of the greatest common factor. Okay, that's kind of a mouthful. What does that mean? Well, I look at these prime factors that are in common. I have a 2. Is there another 2? Yeah, they both have another 2. Do they both have another 2? No. 144 does, but 180 doesn't. Is there anything else that's in common? 3 and yet another 3. So that's telling me is 2 times 2 times 3 times 3, which is 36, will divide into both of them. That is the largest number that divides into both of them. because I've taken all of the common prime factors and combined them together. That is the greatest common factor. So let's say I have 75 and 120, and I want to find their greatest common factor. So I would take 75. What can I divide into 75? 5. 75 divided by 5 will leave me with 15. 5 is prime. Can I split up 15? 3 times 5. Very good. So 75 is 3 times 5 times 5. 120, what can it be divided by? 10. So I have 10 and 12 left. Can 10 be split up? 5 and 2. Those are both primes. I'm going to circle them. 12. 6 and 2. The 2 is prime, so I circle it. 6. 2 and 3. So what I have here, 2, 2, 2, 3, and 5. So there's my prime factoring for, do I have 2 3s? I don't see one. Only one. I only see one. Gotta keep me on my toes, though. So anyway, what's in common? We have a 3 and a 5. So 3 times 5 is 15. That is the greatest common factor. That's the largest number they'll divide into both of those. Next, we talk about multiples. I mentioned memorizing multiples of 8 or 4. What a multiple is it's that number, basically the numbers you'd get if you counted up by that number. 4, 8, 12, 16, 20, 24. Those are all the multiples of 4. The reason they're called multiples is they are created by taking 4 and multiplying it. 4 is 4 times 1. 8 is 4 times 2. 4 times 3 makes 12. 16 is 4 times 4. 20 is 4 times 5, and so on. Just increase the number you're multiplying by 1, and you get this list of numbers. So again, you could list out multiples like that just by making a list. And they'll go on forever because you can keep multiplying by bigger and bigger and bigger numbers. It never stops. So with a single number, multiples aren't very important unless you say, I only want like the first 5 multiples or whatever. Where multiples come in play, just like we had the greatest common factor, we can have the least common multiple, which is the smallest number that both of them share in their list of multiples. Every number has an infinite number of common multiples. Like 3 and 5, well, 3 times 5 is 15. That's a common multiple. You can just keep counting up by 15s, and every one of them will be a common multiple of 3 and 5. So we don't care about the common multiples because there's an infinite number of them. We only care about the smallest common multiple, or the least common multiple. We already mentioned for 3 and 5, that least common multiple is 15. That is the smallest number that's on the multiple list for both 3 and 5. In other words, the smallest number that both 3 and 5 can divide into without a remainder. Well, let's look at something a little more complex. Look at the least common multiple for 12 and 18. This is a little more complicated than the common factor. To do this, we factor them both. 12 is going to be 2 times 6, 2 times 3. So it's 2 times 2 times 6. 18, 2 times 9, and 3 times 3. So 2 times 3 times 3. Why did I put a 6 there in the 12? Maybe 2 times 2 times 3. Correct? So 12 is 2 times 2 times 3. 18 is 2 times 3 times 3. I look at what they already have in common. They both have a 2. They both have a 3. Now I look at what one has that the other is missing. This top number, the 12, has a 2 that the bottom one doesn't. I need another 2 down here. Now they have the 2 in common. Anything else that one of them has that the other doesn't? The 18 has a 3, so I need a 3 up here. Now what I have done is they both have the same factors. 2 times 2 times 3 is 12, times 3 is 36. 2 times 3 times 3 is 18, times 2 is 36. 36 is the least common multiple. Now that's not something we're going to do a lot yet, but when we talk about fractions, talk about least common denominators. Well, least common denominator is just a least common multiple of the 2 denominators. Let's say I give you something like 20 and, let's go 50. And I ask you to find the least common multiple. In your notes, go ahead and find that for me quick. So if we factor, 20 is 2 times 2 times 5. 50 is 2 times 5 times 5. What they already have in common is a 2 and a 5. What do we still need up here? Another 5, right? What do we still need down here? A 2. So if we multiply those back out, they each multiply out to 100. 100 is the least common multiple for 20 and 50. Any questions? Okay, so in your book, page 26, 1 through 63, the odds. Practice the factoring and divisibility rules. We'll give you this next 10 or 12 minutes here to get started on your homework, then we'll take a break, and when we come back, we will do our first test.